best as possible. So like if you guys will end like if you guys don't have any further doubts, then I'll discuss something about deep learning that I thought might be interesting and useful for you guys. So before that, I would like to take your doubts. The way to uh, ask your doubt is either you can type it in the chat box or you can unmute yourself and ask. Okay, I can explain what are KKT conditions. The argument which is KKT is done. Just give me a second. Okay, so I'll first try to motivate why do we need KKT condition and those kind of things. So recall when you used to do calculus in your high school days. I hope I'm properly audible. The fan is not disturbing. If it is disturbing, I'll close it. Can someone please confirm my voice is clear?
Yes, sir. It is audible.
Okay. So when you used to do calculus or finding maximum minimum point in your school days, you always used to do it for function in one variable. Okay, mostly, right? So if you had some f of x, how did you use to find whether a point is maxima or minima? Or given a f of x, how do you calculate the point which is maximum or minimum? Okay, so you had some condition that you used to do f dash x is equal to 0 and calculate all points satisfying f dash x is equal to 0. Okay, so what does this mean? If x is a minima or a maxima, then it must satisfy this condition. Okay, this is what it meant back then. Okay, so these kind of conditions are called necessary conditions. Okay, so whatever you solved was a necessary condition for a point being minima or maxima. Okay, then you used to evaluate f double dash x. If it was greater than 0, you used to say that it is a minima. If it was greater than 0, you used to say that it is a maxima. If it is 0, you can't conclude a much, or in two dimension, you used to say that it's a saddle form. Okay. So along those lines, these two conditions together were your sufficient conditions. Okay. These together were your sufficient conditions. Okay. Now in machine learning, the kind of function that you encounter are not actually functions of one variable. Okay. They are functions of several variables. So for that, I think what we did in this course was we characterized something similar. So if you have f, a function of let's say x1, x2, xn. So let's denote this x1, x2, xn by a vector called x. Okay. Now for this, you have a similar condition that if your gradient at that point is 0, this is a necessary condition for, right? Necessary condition, and a sufficient condition was that your Hessian, that is the second derivative, is positive semi-definite. These kind of conditions we had. Okay, so in this course, before starting KKT, we looked at functions of this form, and what is the necessary and sufficient condition for optimal values of these kind of functions. Okay. So if you look at a general optimization problem, that looks something like this. Okay. So you will have a statement that you want to minimize or maximize. Okay. Subject to some constraints, right? Earlier, what we just had a function that we wanted to maximize or minimize. We didn't had any constraint associated with it. Okay. So whatever we derived above, whatever we talked about above, won't work for this kind of optimization problem. Okay. So for this kind of optimization problem, we have something called KKT conditions. Okay. Which are your necessary condition for a point X to be an optimal point. Okay. So for example, here you had gradient equal to 0. In the above condition, you had f dash x is equal to 0. Similar to that, you have your KKT conditions, which are necessary conditions. Okay. So, okay. So what is the statement for these KKT conditions? First thing that you assume is that your x dash is a feasible solution. So you can only check this thing for a feasible point. That is, your x dash satisfies these constraints. Okay. We will include that in KKT condition, but just to give you an intuition, we are doing these things only for feasible points. Okay. So x, so point in feasible point is a local optimal point, then it will satisfy these KKT conditions. So these are your necessary conditions. Okay. So what is this necessary condition? Let's look at these necessary conditions one by one. Okay. Okay. So first condition is that the gradient of x at a point, that this is same as whatever we had over here, the gradient being 0. So we have gradient. Okay, somebody is joining. So we have gradient plus we also have gradient of all the constraints multiplied by something that you see over here as lambda I. These are called Lagrange multipliers. Okay. So there should exist some lambda i's such that if you multiply them with the gradient and you take the sum, that should be equal to 0. Now, rather than having just the gradient equal to 0, you have an updated condition for constraint optimization. Okay. If you look at the second condition, this is just the feasibility condition. This is same as, okay, so just a second. Yeah. So if you look at this condition, this is same as your feasibility condition that was already mentioned over here. Okay. So we have a most important condition over here, the third condition, that is called complementary slackness property. Okay, or the complementary condition, which says that lambda i's that you have found multiplied by g i's, this should be equal to 0. Okay. So what does this say is, you can either be on the boundary of this gi constraint. Okay, that is your gi is equal to 0. Otherwise, your lambda I should be equal to 0. So whenever you study LPP or those kind of things, then you will appreciate that they are just looking at the active constraints. So this condition that they want to satisfy, the first condition, they want to satisfy this only on the active constraint. That is where your g of ix is equal to 0. Okay. And the last condition is pretty simple. That is lambda I greater than equal to 0. Okay. So these four conditions together make something that is called as KKT conditions. Okay. So we have talked about necessary condition. We also had some sufficient condition. Okay. So for general optimization problem, we actually don't have any solid sufficient condition. Okay. So we don't have explicit sufficient condition, but in some special cases, we have some sufficient condition. What are those special cases? That special cases, if your f and g are convex differentiable functions. So differentiability is because you want to calculate the gradient. So it should be differentiable. But if your f and g are convex, this is the important point, that your f and g are convex. Okay. If they are convex, then these four conditions that we just talked about, this necessary condition also becomes its sufficient range. Okay. So this is what is your KKT conditions. Was I clear? Was I able to clear your doubt, or if you have anything else to add over here, you can ask. Okay. Any other doubt? Any other person have? Okay, as nobody is asking anything, like if you have doubt, you have started typing, please type it and ask. But in the meanwhile, I think I can start. Like, if you have doubt, you can stop me in between, and I'll be happy to clear your doubts, because that's what this session is meant for. But because other people have also joined, and just we don't want to just sit idle. So let's say if we want to do, if we can do something. Okay. Okay. So you might have heard of this. Okay, again, just to repeat, if you have doubt, please unmute yourself and you can ask, or you can type it in the chat box. That is also fine. Okay. In the meanwhile, I'll try to give some insights about this area called deep learning. Okay. So this course is called Essential Mathematics for Machine Learning. Okay. So we have talked about some machine learning models like linear regression, right? Logistic regression we discussed. Okay. And we also talked about SVMs, right? Support vector machines. But these days, if you look at the buzzword or the area that is dominating the machine learning field, is actually the deep learning models. Okay. So I thought this might be a good topic to discuss if nobody has anything to ask, because from past experience, what I've seen is very less people ask out in this kind of session. So I sort of thought I'll very briefly discuss what are deep learning models and those kind of things today. Okay. So I'll draw a figure. Okay. So this is a broad area or broad umbrella called artificial intelligence. Okay. Where you want machines to have some kind of intelligence. Okay. That is the word that you hear, that is AI or artificial intelligence. Okay. A subset of AI is something that is called machine learning. Okay. So these days, if you talk about AI and machine learning, they are sort of one and the same thing. But if you talk in principle, this is actually a subset of AI. Machine learning is a subset of AI. There can be other methods which are non-machine learning based, but today when we talk about AI models, they are all are machine learning based models. Okay. So a subset of this is machine learning, where you want machine to learn from data. Okay. And a further subset to machine learning is something called as deep learning. Okay. Or the DL. Okay. So this is a further subset. Here you only work with a particular type of architecture. Okay. So what is that motivation behind that kind of architecture that we are going to talk today? Okay. So this is the broad categorization. You have AI, which is a superset of ML, which is again a superset of deep learning. Okay. Okay. So it is very hard to think that you might, like some of you might have not seen any application of this deep learning. Most of you would have seen some application or other of deep learning. So this chat GPT, this DALI-E, all those are based on these deep learning ideas. Definitely more complicated model than what we are going to discuss today, but they are based on this kind of idea. Okay. So if you look at the history of deep learning, the first application that it tried to solve or was meant for was handwritten digit recognition. Okay. So the problem was that when you send a letter or a postcard back in those days, so people used to write a pin code. Okay. Let's say they write a pin code like this. So when people used to manually sort it, it used to take a lot of time. Okay. So what was the intuition behind this? That if I click a picture of the address, then a model should automatically figure out to which area this pin code belongs and hence route it to that particular area. Okay. So the first problem that we tried to solve using this method was handwritten digit recognition. Okay. So there is a very famous data set called MNIST data set, which has these handwritten digits and the corresponding labels to it. Okay. Now machine learning has developed a lot. So there are many tasks like object recognition. You have to recognize object and classify those objects. Okay. Text generation you have, right? Image generation. So there are many such applications. Okay. Action recognition. You have to recognize what is the action happening in the picture. This person is diving. This is golf swing, kicking. Okay. Machine translation is another very important task. And you can these days can model many tasks using these deep learning models. Okay. So what was the idea behind this deep learning model? Okay. Okay. So what we say is this was sort of inspired by the structure of neurons in our brain. Okay, this is what people say. Okay. So what happens in a neuron in our brain? Let's say this is a neuron. Okay. It will have many entries. Okay. It will have many entries. It will do some computation on it. So whatever entries that it receives, it will do some computation on it and pass on the message to next neuron. Okay. So there would be a very large network of neuron. So let's say there is one more neuron over here. Okay. And there can be a very large network. So in our brain, we have millions and trillions of neurons connected to it with each other, and they just pass messages to each other. Okay. So the first attempt was to understand the structure of one of these neurons. So before we want to look at the network of neurons, okay, we just want to look at the structure of one of the neuron. By the way, the name neural network comes from the fact that we are looking at a network of neurons. Okay, that's why it is called neural network. So this neural network, deep learning, okay, sometimes it is also called multi-layer perceptron. Okay, these all are same name for these are all same name for the same thing. So neural network, if you say neural network or deep learning, you are referring to the same thing. Same way, if you are talking about deep learning or multi-layer perceptron, you are referring to the same thing. So it's the same three different name for the same thing. Okay. So now let's try to look at the structure of a single neuron. So how does the structure of a single neuron looks like? Okay. Okay. So if you recall our course, we discussed something called linear regression, right? We did something like linear regression. What we did over there was, so we had some feature, let's say x1, x2, yeah, x3, let's take only three feature for the time being, right? What we wanted to do is, we wanted to learn W1, W2, W3 and W4, right? Such that we minimize some loss function. Okay. Our goal was to find W1, W2, W3, W4, so that this is as close as to your Y, whatever you want to predict. And then you used to take a difference between Y and this, then probably square, and this was your loss that you wanted to minimize. Okay. Now, if you look at this part, okay, this is a linear combination of x1, x2, and x3, and hence is a linear function of your features. Okay. But in real life, your data generally is dependent on your prediction function in some non-linear way. Okay. So we talked about kernel functions towards the last, right? Along the same motivation, it is possible that this data is dependent in some non-linear way. Okay. So what does this people suggesting perceptron or neuron did is, on top of this calculation that you have, they added some non-linearity. So what kind of non-linearity? Your non-linearity can look something like square. Okay. So rather than taking the loss between y and this sum, you take loss between y and square of this sum. So right, so you can have w1 x1 plus w2 x2 plus w3 x3 plus, sorry, yeah, and square of this. This is the loss, and then again square for the loss term. Okay. So this is some sort of non-linearity that you have introduced, right? This non-linearity that you have introduced in the deep learning literature is called activation function. Okay. Given the background, let's look at how does the perceptron looks. Okay. So a perceptron calculation has two steps in it. Okay. Just try to relate it to whatever we discussed about linear regression. Okay. So a perceptron will have some inputs, that is x1, x2, x3, x4. These are nothing but your features, right? X1, x2, x3, x4 are your features. And it will have only one output. Okay. Also, every branch that you see a line going from x1 to this circle. Every branch will have a weight. Okay. So W1, W2, W3, W4. Okay. And when this data goes inside this circle, it has two operations. One is sum, and then is some nonlinear activation. Okay. So first I'll define what is sum operation. What does this sum operation do is, it just takes x1 multiplied by w1, okay, adds it to product of x2 plus w2 plus x3 plus w3 plus x4 plus w4. Okay. And also, yeah, this is what it does. Okay. And this is the plus operation. After you have calculated the plus operation, let's call this as sum, because this is sum. Let's call this as s. Then your phi operation finally does phi of s, and this is your output. Okay. This phi function can be something like your square, as I mentioned before. Okay. So this is very similar to linear regression if you see. The only extra thing is that you are passing it through some nonlinear activation function. Okay. Okay. So any doubt till this point? Yeah, if you have any doubt, you can please ask. Okay. So now when we have developed so far in deep learning literature, okay, we know many types of this activation function, right? But initially when it was proposed for something called as threshold activation function. Okay, so it was a sort of thresholding function. So its graph looked like something like this. Okay, so what is phi of x? Phi of x was actually a nonlinear activation function. If your x is greater than 0, then it takes value 1. Okay. If it is less than 0, it takes value 0. Okay. This was the phi which was initially proposed. What does this say? So if your this s, so phi of s is given by 1 if your s is greater than 0. So whatever is the sum that you're obtaining, if this thing is greater than 0, it will output 1. If it is less than 0, then it will output 0. Okay. So now you can relate, I think, this to the classification task that we did. Okay. So if you have two classes, okay, two classes, this is very similar to logistic regression that we did, right? So the curve that you had in logistic regression was slightly smoother than this, right? This is more sharp because logistic regression is more advanced. Although deep learning is doing very well, we will see why it is doing very well. But logistic regression is slightly newer as compared to this. So this is differentiable and those kind of things. But when this single perceptron was proposed, this phi activation function that was proposed was not differentiable, and it has this kind of structure. Okay. So there are very few small things that I want to mention over here. So because this was not differentiable, you can't optimize it via gradient descent and those kind of methods that I suggested when you have logistic regression or SVM. You can use those kind of optimization methods. But when you have a non-differentiable function, you can't use something like gradient descent. Okay. Also, this back propagation and gradient descent was proposed much later than what after this threshold came. Although this gradient descent was known much before, but in context of learning theory, it was proposed later. Okay. So what these people who proposed this perceptron thing did is, they also proposed an update condition. Okay. And this was the update condition that they gave. Okay. So this is not very relevant in today's context as nobody uses this kind of update condition, but just because it was proposed in history, we should study this. So the new weight is given by, so this W is a vector of W1, W2, W3, and W4, right? This is given by W plus, so this is your original label, and this is your predicted label based on phi of s. So either it would be 0 or 1, right? Multiplied by xi. Okay, so this is the update condition. So if you are making no error, that particular data point will make no change in your W. When you are making an error, you will update your W. Okay, and then again make prediction for other points and see. Okay. What was very interesting about this proposed method was that it was theoretically proved that if you have a linearly separable data, I think all of you know what is a linearly separable data by now, this method will converge. So this would be able to separate your data points. After some time, it won't be able to separate your data points. Okay. 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 So any doubt in this? If you have any doubt, please ask. Okay, somebody had written some question. I sort of missed. I'll look at that question. Let there be 20 patterns for linearly separated Okay. Okay, I'll cover this question. Just in a while, I'll cover Dr. Prashant. Okay, so any doubt in this, what we are discussing, linear separability? Okay, so this perceptron idea. Okay, so I'll just give you a motivation, and then I can take the question that Dr. Prashant Patil has asked. Okay, so you might know about a function called XOR function. Okay, so here what I had is, so when you have binary features, okay, so you have this OR and AND function, right? You might know, either you would have studied in physics, or if you, some of you have some computer science background, you might not know this OR gate, AND gate, and those kind of things. Okay. So using the kind of perceptron that we sort of studied right now, it is known that you can represent OR and your AND function. Okay, so you can represent, choose a particular value of W0, W1, W2, so that this perceptron becomes your OR function, and similarly it becomes your AND function. Now the next question was, can it represent all binary functions? Okay, so by all binary function, I mean whose input are binary and output is also binary. Okay, turns out there is a very common function called XOR function. So for it, which if you have 0, 0, answer is false. If you have, okay, so this is 0, this is 0, this is 1, this is 1. So if one of them is 1, then your output is 1. If both of them are same, then the output is 0. Okay. Now, if you look at this example, this is actually not linearly separable. Okay. This is not linearly separable. No matter where you draw a line, you can't separate these 4 data points. These are those 4 data points that you can't separate. So when people tried finding a perceptron to sort of classify this kind of data points, they failed. Okay. So they failed. So this is a limitation of perceptron, that for even very simple nonlinear classifier, they can't converge, right? Because they would just draw some lines, and there is absolutely no possible line which can separate these 2 data points. Okay. So what is actually possible is, okay, what is possible is you draw a line, okay, rather than drawing one line, what you can do is you can draw 2 lines. Okay, I'll try to draw those lines. One line can go from here, other line can come from here. Okay. So this yellow region means that for the first line, this part is positive. Okay. And for the second line, let me use some other color, that is this blue color. I think I have made a mistake here. Yeah. Okay, sorry. So just a second. We can take something like this, or no. This. We draw a line like this. Now I think it's fine. Okay. So there, this is the positive part of this line. Okay. This is the positive patterns. So what I'm saying is you can't separate them by just one line, but based on condition on two lines. So if you look at this condition, you can say that if both lines are either positive or both lines are either negative, then you have plus label. Okay. Otherwise, you have zero label. So what you can do is you can represent this as a combination of two perceptrons. So one perceptron can be used to find this particular line. So one perceptron can be used to find this particular line, and another perceptron can be used to find other line, and then these two perceptron can be further merged using the third perceptron, okay, to get the output. So the way to handle this nonlinear functions is via combinations of perceptron. Okay. So you should not just look at one perceptron, but combinations of perceptron. Okay. So before actually going into neural network, I'll just take the question that someone has asked. Just give me a minute. I know from where you are referring to this question. This probably is from the second last lecture. I'll just take that slide and clear things. Okay, so just a brief thing why this question is framed like this. So before this AI and ML high, there was a area called pattern recognition. So this classification and regression, what we study today in ML and those kind of things, it was studied in the area called uh, this pattern recognition. So the data points over there were called patterns. Okay. So I think the professor used those kind of notation for the last two lectures. That's why in the question you have these patterns and those kind of ideas. Okay. So I'll just give me a second. I'll share a different screen. I think the person, okay, it is back. Okay, so if you look at, am I audible, Dr. Patil? I think I should be. Yeah. So if you, this is the slides from the lecture. If you look at the wording of this,
So this is
yeah,
question from last assignment. It is.
I got your point.
Yeah.
Yeah. So if you look at the wordings from in this particular slide, I think this is from last assignment only. So it says that let Xi's belonging to Rn be the set of finite patterns. So in this question, what patterns mean actually is data points. Okay. So when the question says let there be 20 patterns for linearly separable binary class problem, so you have 20 data points. Okay, this is one thing. And now the question is, then the total number of constraints in the dual optimization problem corresponding to hard margin classifier is this. Okay, so let's look at the dual formulation that professor has written. Okay, he has not included it here. Yeah, this is the dual formulation. Okay. Just a second. Yeah. So this condition that you have, the summation of alpha I to xj, this is a summation from I is equal to 1 to m. Okay, where m is your number of data points. Okay, so you have m data points that was mentioned over here. Okay, so this condition that you have, this summation from I is equal to 1 to m. So this m is your number of data points. That is the number of patterns that is mentioned. Okay, now if you look at the dual formulation, okay, so how many constraints it does have? So it has 20 constraints from here. That is that alpha ATI is equal to 0, and 20 this inequality constraint that your alpha I should be greater than equal to 0 for all n. Okay, so I think it should be 40 constraints should be the answer of the question that you are asking.
So, but in the assignment, the given it is answer as 1.
The answer that they have given is 1.
1.
Okay, so okay, one more thing. So there is something called excluding the non-negativity constraint that you have mentioned. So this 20 constraints we can remove. I'm really sorry. Okay, I'm really sorry. So if you look at this constraint, this particular constraint, this is summation from I is equal to 1 to m is equal to 0. So let's say if there are two data points, so this constraint would look like alpha 1 d1 plus alpha 2 d2 is equal to 0. So this is not 20 constraint, I'm really sorry, but only one constraint that you have
Yeah.
divided over 20 points, right? And these are called your non-negativity constraints.
Non-negative.
So they have explicitly mentioned that you should not consider non-negativity. So there is no point.
Oh, thank you. And if possible, please solve one question on a KKT conditions. How to solve it.
Okay, I have a question. I will solve. It was week 8 or 9, I guess. Yeah. I don't. Just a second. Yeah, I will try to solve it. So this is the question that we have. Okay, I'll zoom in this. The question says, this is the minimization problem. Okay, and alpha comma 9 by 2 is an optimal solution. Okay, then we have to find the value of alpha. This is the question that we have. So this would use KKT condition. Okay, now just a small thing to check. We mentioned that this is a sufficient condition only if f and g are convex differentiable functions. Okay. Now this is your f, this is your g, right? Yeah. Now if you look at your g is actually a linear function. Okay. So all your linear functions are convex in nature. So nothing needs to be checked there. So if you look at your f is a quadratic function. Okay, so you remember there is a specific format of quadratic functions plus some qx plus some s it can have. And if your P matrix is positive semi-definite, then it is a convex function. So first thing that we should do is to check whether the problem that we are trying to solve, f is convex or not. So if we try to write its, yeah, the P matrix, it would be 4, -2, -2, and 2, right? And if you look at all the leading principal minors, this is 4. 4 is greater than 0, right? And its determinant is 8 plus 4, 12. That is also greater than 0. So both the leading principal minor is greater than 0. That's why this is a positive definite matrix and hence a positive semi-definite matrix. So this problem that is given to us, sorry, is actually a convex optimization problem. So we can use KKT condition. So what does this mean is that if this alpha comma 9 by 2 is an optimal solution, then this should satisfy the KKT condition. Okay. Now we have 3 constraints over here. Okay. If you look at the sample problem, all the constraints should be of form gx is less than equal to 0. So we should write it in that form first. So this is minimum. Okay, I will change the color. This is minimum, right? 2x square minus 2xy plus y square minus 5x minus 2y, right? Subject to 3x plus 2y is less than equal to 20, minus x is less than equal to 0, minus y is less than equal to 0, right? Now what is the first condition? That this sum should be equal to 0. Okay. So we can start with the easier condition, that is condition 2. Let's start with. Okay. So because this is a optimal solution, so it should satisfy all the KKT conditions. So let's start with condition 2, which says gi of x bar is less than equal to 0. So if this is your solution, then 3 times alpha plus 2 times 9 by 2 should be less than equal to 20, or 3 alpha plus should be less than equal to 11. Okay. So alpha is less than equal to 11 by 2. This is one piece of information that we have got from this particular condition. Okay. Other condition, like other information that you can get is alpha is greater than equal to 0, which is okay. This is also what we have got, that alpha is greater than equal to 0. Okay. Now let's see what we can do. Okay. Let's look at the third condition and see if we can get something out of it. So what does this my third condition say? That uh, lambda I multiplied by gi of x should be equal to 0, right? So lambda I, so let's take lambda 1 multiplied by, yeah, lambda 1 is okay for this. This is 3 alpha. Again, 9 by 2 is 9. 2 multiplied by 9 by 2 is 9. This thing should be 0. Okay. And what does this say? lambda 2 multiplied by x, x is your alpha, this should be equal to 0, right? And then again, lambda 3 multiplied by 9 by 2 should be equal to 0. From here, what we can infer is that this lambda 3 that we have over here, this lambda 3, just a second, yeah, lambda 3 becomes 0 from here, okay, because it's a product of two things that is equal to 0, so lambda 3 should be 0, okay. This is one piece of information that we have got. Okay, so this equation gets modified as 3x plus 2y minus 20 is less than equal to 0. So we will have a minus 20 also. Right? This also miss minus 20. That would mean that lambda 1 multiplied by 3 alpha minus 11 is equal to 0. Okay. Now let's see what we can have from the first condition, that is our gradient condition. First condition says you take the gradient of f plus sum of gradient of all the constraints, right? This should be equal to 0. Okay, let's look at what is the gradient of x. Gradient of x, I'm writing here, gradient of x is nothing but, I'm writing here, right? Gradient of x is nothing but, sorry, gradient of, what do you want to call it? F, sorry, not x, right? With respect to x, this would be 4x minus 2y, right? And with respect to y, it's 2y minus 2x minus 2. Here we have minus 5 also, right? This is your gradient of x. Now we know the value of x and y, so let's calculate this at this particular point, alpha comma 9 by 2, right? So this is 4 alpha minus 9 minus 5, right? This is 2 times 9 by 2 is again 9 minus 2 alpha minus 2. So this is 4 alpha minus 14, and this is minus 2 alpha plus 7. This is your gradient. Okay. For others, we can calculate on the go because those are just linear functions. Okay. So this is 4 alpha minus 14 minus 2 alpha plus 7. Then you have lambda 1 times. So the gradient of this thing would be 3, right? Because x get cancelled, this is 2. This is 11 by 3. Okay. Plus lambda 2 times, this is minus x comma 0. So this would be minus 1 and 0. Right. And you already know that your lambda 3 is 0. So you can just ignore that term. And this is equal to 0. Okay. So now we have to solve these equations, whatever information that we have received. We have to somehow solve this set of information that we have to obtain the value for alpha. Okay. One thing that we were able to eliminate was that my lambda 3 is 0, right? Other conditions that we have is that, yeah, lambda I should be greater than equal to 0. The product should be equal to 0. And these constraints should be satisfied. Okay. Okay. So let's see what can happen. Now there are two possibilities. Okay, let's look at this condition. I'll change the color to green. Let's see what is highlighted in green. Okay, we know that lambda 2 times alpha is equal to 0. Okay, so there are two possibilities. Either your lambda 2 is 0 or your alpha is 0. Right? There is only two possibility. Now consider the situation that your alpha is 0. Okay, if your alpha is 0, what would it mean? Alpha being 0 would mean that this is 3 times 0 minus 11, right? That means minus 11 times lambda 1 is 0 or lambda 1 is 0, right? So if I had alpha is equal to 0, then my lambda 1 becomes 0. Okay, and what happens next? Next thing that happens is lambda 1 goes to 0 over here. Okay, so I have minus 14 and 7 plus lambda 2 times minus 1 comma 0 is equal to 0. This statement is absolutely not possible. If you look at the second row, this is 7 plus 0 is equal to 7, right? So this is actually not possible at all. Okay, so that means this condition that alpha is equal to 0 is not possible. So only option that we have left is your lambda 2 is equal to 0. Okay, so we can just eliminate this thing that your lambda 2 is equal to 0. Okay. Okay. Now, similarly, if we look at this condition, okay, so this says that lambda 1 times 3 alpha minus 11, right? This thing is equal to 0, right? So either lambda 1 can be 0 or this second quantity can be 0, right? So now if my second quantity becomes 0, that is 3 alpha minus 11 is 0, that means my alpha is 11 by 3. Okay, let's try replacing this over here. So this is 44 by 3 minus 14, right? Now my lambda 1 is non-zero. So plus lambda 1 times 3, this thing is 0. Okay. And the second quantity is minus 2 times 11 by 3 plus 7, right? Plus 2 lambda 1 is 0. Let's say if this is a set of possible feasible solution. Okay. So this would mean 14 3 is 42. So 2 by 3 plus lambda 1 times 3 is equal to 0. Or lambda 1 is minus 2 by 3. So this would be minus 2 by 9. Okay. And what does this second statement say? So this is minus 22 plus 21 by 3 is equal to 2 lambda. Sorry, plus 2 lambda is equal to 0. Okay. Or this would mean that 1 by 3 is equal to 2 lambda 1, or lambda 1 is equal to 1 by 6. So you see that these two statements or these two linear equations can't be satisfied together. Okay, so we can't have this 3 alpha minus 11 is equal to 0, and hence lambda 1 is also 0. Okay, so we took some effort in proving that lambda 1, lambda 2, lambda 3 is 0. So this term also gets cancelled out. So this term becomes 0. So what we are left with is 4 alpha minus 14 minus 2 alpha plus 7 is equal to 0. Or this would mean alpha is 14 by 4 or 7 by 2. And the same thing you will get from the second equation also. So this is 7 by 2. So this is how you sort of use your KKT conditions. All these conditions will give you some information or the other. You use them to reach to a final goal. This was a solved example on KKT conditions. Any other doubt that you people have? Would be happy. Okay. If you don't mind asking Dr. Prashant Patil, what was the area in which you work actually? What is the area in which you work?
I am a lecturer in engineering college.
Okay,
I do work on graph theory actually.
graph theory. Okay, so mathematical perspective.
Yeah, from background is mathematics.
Okay, so my research area is also graph machine learning. So applying machine learning to graph data when you have data in form of networks.
Fine.
Yeah.
I will keep you posted.
Okay. Okay. So if you guys have doubt, you can keep asking. I'll just finish this multi-layer perceptron motivation that I started. Okay. So we saw to a point that we had something called perceptron that was proposed. Okay. And then we saw example which we can't separate via perceptron. Okay. So what we suggested is we will use multiple perceptrons together. Okay. So this kind of setup is called multi-layer perceptron. That is multiple layers of perceptron you are using together. Okay. And this later came to know as later we know this as deep learning or neural network, because this is also a network of neurons or perceptrons. Okay. Okay. So this is a modern sort of architecture of your multi-layer perceptron or feed-forward neural network. You have some features, that is x1, x2, add choice of color. No. Yeah, x1, x2, x3. Okay. So you pass it to some perceptron, right? You pass it to, let's say this is called perceptron 1. You pass this information to perceptron 1. It will do some so it will have associated weight W1, W0, W1, W2. It will do some calculation, pass it through some activation function, and pass on the result. Okay. Similarly, now next perceptron will have some other weights, right? And it will also take some input. So like intuitively, if you see the first perceptron try to capture some pattern in the data, perceptron P2 sort of tries to capture some other pattern in the data. Similarly, some perceptron P3 will capture some other pattern in the data. And in the next layer, we sort of merge them to combinedly capture some other information. So there can be multiple hidden layers, and then there will be some output layer. Okay. So this is a general architecture. So let's say this is your x1 and x2 are your input. Okay. What would this okay. So what would happen? in order to reach over here, it will again have two operations, plus and sigmoid. Okay. So what will plus operation do? Plus operation will do x1 multiplied by w111 plus x2 multiplied by w121. Okay. And then this would be passed via some nonlinear activation function to obtain the result. Similarly, you can obtain the output for this. Let's say we call this O1, we call this O2. Then in the second layer, over here we will have O1 multiplied by W 1, 2, yeah, and O2 multiplied by W1, 2. Okay. Yeah. So then you will get this output over here. Let's say this is O3, this is O4. Then you combine them together to get the final output. So one thing you might have noticed is that there are many parameters. So 4 over here, 4 over here, 8, 2 over here. So 10 parameters that you have to learn just for 2 input features. Okay. As compared to 2 features that you used to learn in your linear regression. Okay. So there is a large increase in number of parameters that you have to learn. Okay. Hence, it is computationally much more expensive. Okay. So even if you do gradient descent, when you are calculating the gradient, the vector would be some of length 10. Okay. And similarly, other components also becomes computationally expensive. You have to do some calculation over here for the next layer, then for the output layer. This is just a 3-layer, 2 hidden layers. Okay. If you look up these modern applications that does this image processing and those kind of things, they will have thousands and thousands layers. Okay. So there is a period in which like this perceptron was proposed much earlier, but for a large time there was not a lot of progress in this area of artificial intelligence and neural network. The reason was the kind of computational challenges that these methods proposed. Our computational requirement, our machines were not ready for these kind of models. Okay. Then there was a lot of development in computational aspects, that there were this GPUs coming up. Okay. People proposed faster way of this gradient descent and those kind of things. That's when this neural network then again caught hype. Okay. And now it is very famous. Okay. Because of the computational issues, it was not very useful for a large amount of time. Okay. So yeah. Again, so there is some method, something that is called back propagation. When you do a deep learning method, you will sort of encounter this method called back propagation. And this is the most common way to calculate the gradient. Okay. So the weight update rule is very simple in neural network. This is just W minus some lambda times gradient. But how you calculate gradient for such a large network is done via back propagation. This is just application of chain rule that we study, but a more sophisticated way of writing it so that your computations are easy. Okay. Now somebody asked, could you explain how to solve an optimization problem, like the general process of solving it? So the answer is there is no general process of solving an optimization problem. Okay. So still there is a lot of research going on, like how do we, like people are not even trying right now to solve any, like find a method that can solve any arbitrary optimization problem. So if you look at the regime of optimization problem, okay. So it can be classified on the basis of two things, whoever asked, J. Bakshi. Okay. So one is linear programming. Okay. Another is non-linear programming. Okay. So in linear programming, you have methods like simplex method. Okay. which I think still is the most common method that people use to solve optimization problem. So to answer your question, there is no straightforward same rule that can be applied to every optimization problem. So different kind of optimization problem have very specialized kind of rules that you use. Also, like if you have some structure in your problem, okay, you can have faster optimization problems, which can take lesser step to convert those kind of things. Okay. And in the non-linear programming, if you have a quadratic programming, you still have some things that you can do. For others, it's a very open space. Specific problems have specific solution. You can find you can check whether a point is a optimal point or not by KKT conditions. And if your F and G, as I mentioned, are convex, then you can also use KKT conditions to find the optimal point, right? Apart from that, it's a very open landscape with not lot of concrete fixed methods. Okay. So yeah, like if you want to dive deep into it, what kind of methods are there, then you will have to take some optimization course. I can just give you the idea right now that for linear you have something called simplex. You have something for quadratic programming. You have something for integer programming. You have something for mixed integer programming. So there are many different regimes of optimization problems and many different like tricks to handle those kind of problems. Okay. Now you will say, then how do we optimize this? Like how do we tackle optimization in machine learning setup? So if you look at the problems that we encounter in machine learning, okay. So we have stick to something called as gradient descent. So most of the machine learning algorithm that you see has stick to gradient descent or some variants of it. Okay. So gradient descent is not a very fast method. So there are some alternatives to it to make it faster or to guarantee it to converge to some point. For example, Adam, okay, Adagrad, right? So these kind of variants exist. Okay, but I'll give you the basic idea how does this work. Okay, so in machine learning, what you have to optimize. Okay, the thing that you have to optimize is your loss function. You have to minimize your loss function. Okay, so let L is your loss function. If L is your loss function, like if your weights are given by W, right, then L is your loss function. So you initially take any random weights. Let's call it W naught. Take random weights. Okay. Then you calculate the loss and the gradient of your loss. Then what you will do is calculate gradient of L with respect to W at this point, W naught. Okay. After you have calculated the gradient, you will do a gradient descent update step. So your W1 would look something like W naught minus some lambda times gradient of W at n. Okay. So this is the basic rule that we sort of follow when we try to optimize loss function in machine learning. This is the method that we use. Okay. And this in general will work very well. Okay. If you have any arbitrary loss function also, which don't have any constraints, this would work very well. The only problem is the convergence is not actually guaranteed. Okay. Also, when it converges, it might land into local minimas. This is a bigger problem. Okay. So now I told you that there are some alternatives to this gradient descent method. What are those alternatives based on? So they sort of modify this rather than just using gradient in that particular step. Some people suggested that we can use gradient from previous steps also. that can in some sense help us avoid this local minima. Okay. Also, some people have suggested that this lambda, rather than keeping it fixed, we can make this adaptive. Okay. So yeah, so these two things people have tweaked and have come up with different variants of gradient descent. That is the most general approach that people take to solve optimization problem in machine learning setup. Okay. So if you talk mathematically about random functions, there is no fixed method to solve any arbitrary optimization problem. There are a lot of people working in this research area trying to find good methods for some particular type of problems. I hope I was able to answer your question. Okay, any other doubts you have? Okay, if there are no other doubts, I think we can end this session. Okay, because this was a doubt